All right, so let's get this going here. Actually, I'll show you this first. So have all the exams graded. You should kind of see what your score was up here on Canvas. I then identified kind of for every student kind of what your highest and lowest exam scores were, and then kind of weighted them as though they're going to be your best two exams. So still kind of, I don't want to say worst case scenario, but if you didn't do well on one of the exams, right, it's going to end up being weighted still a little bit more than potentially it could be at the end of the semester. So I identify your highest, weighted it by 30%, lowest by 20. I think I have everything. I've got all the Excel assignments graded. I think I have any excused absences built in here for the iClickers. So grades should be kind of up to date at this point. So if you have any kind of questions or concerns over anything, please reach out sooner rather than later. But I think we should be kind of all caught up in terms of what you're seeing on Canvas. Okay. I might kind of at the end hand out kind of your exams, and then just kind of you can leave when I give it to you. Also helps me kind of get some names down a little bit better. You'll have your Scantron. I'm still waiting to kind of post probably the answer key until this afternoon. So once I'm done with teaching all my classes, I'll put the exam as well as the answer key up there so you can go through if you want to kind of figure out exactly which ones you got incorrect. If you want to kind of work through that, because we're going to continue with hypothesis testing. Okay, so make sure I'm recording this. I am. All right. So I also have kind of the next kind of put week 13, right? So we'll start this today and then we'll kind of pick up with it next week. Okay? So we left off with confidence intervals and hypothesis testing. What we were doing this for was always one population. First of all, before I get going, is there any questions for me related to anything course-wise or distance-wise? Okay. Overall scores were pretty decent. I think there's a couple that are still in the class that aren't showing up and taking exams. So if I take those out, the average was just above a 70, right? Floating right above a 70 there. Grades overall in the class right now look pretty good. I think the average grade, even kind of including some of those people who are didn't take the exam, are still right around just below an 80. Right? I think the median actually is maybe slightly above 80. Right? It's like an 81 or something. So overall, pretty good. Typically on the final, usually the second exam tends to be the worst. A lot of people can really help boost their grade in that final, and making sure that they replace a heavy-weighted grade or heavy-weighted exam with a better score. So we're in a pretty good spot in terms of where I usually see grades. So we left off with hypothesis testing and confidence intervals, and we're going to pick back up, do some more examples of that, and then we'll have one more topic, which is regression, that will kind of take us into that final. So over the next month or so, right, we'll really only have kind of two topics. Now, there's various parts to each one, but so what we're now going to do, something we started to try to do with one population examples, were things like, maybe I saw the sample mean in 2010. I saw the sample mean in 2015 was higher. I built a confidence interval for both of these, depending on whatever example it is. And if they didn't overlap, I could say that with whatever level of confidence, this variable, where we're looking at, was higher in 2015. So that is a way for me to kind of walk us into, it's not technically correct if we don't have similar sample sizes. Okay. So we're going to now talk about how do I actually test for differences between 2 years, between 2 countries, between, whatever it is. So we weren't quite doing it correct before. We were just seeing if the confidence intervals overlap. It's very close, but we need to be a little bit more correct. So we're going to have 3 different types of examples, right? Today we'll focus on one. So we can build confidence intervals, or we can do hypothesis testing for basically the same 3 that we were doing for one population example. It's just now we'll have 2 populations. So I can test for the difference in means when I know population variances, the difference in means when I only have sample variances, and then the difference in proportions. So now we're just thinking about comparing the 2 groups, and can we actually do some confidence intervals and hypothesis testing for what the difference is between those 2 groups. That's a lot more powerful, right? It's interesting, I guess, to know where the value of certain variables are, lay, but in practice, usually what we're more concerned with, have things increased over time? Are there differences between groups, right? This is a lot more useful, I would say. But we have to understand when populations to get here. And then we'll do something called matched pairs. I'll kind of hold off on talking about that until we actually get there. It's a little bit different, but actually really it's a little bit easier than some of this two population stuff that we'll start out with. So it's kind of our motivating examples, right? And don't worry about writing these down. We're going to go through each one in particular, but just kind of set us up. You know, maybe I've got two different majors. I've got their starting salaries, and I want to know with 95% confidence, can I say that, you know, one major makes more than the other? Here I think I chose econ and theater, maybe. Yeah. Right. Another example would be I've got a survey. I conducted it in 2 different years. I was asking about the favorability of a certain policy. Over time, did the favorability of that policy increase? Did it decrease, right? Or has it changed at all? Then I got another one, right? Thinking about kind of texters and non-texters while driving. I've got the response time in seconds. While you're texting while driving, do we see a difference in response times? Right? So these all seem like very real like applications, right? These seem like questions we might want to answer. So how can we get it, right? Well, we've got two populations. You think about it this way, if I had econ theater majors, I'm going to have 2 samples of each major, right? So I can calculate 2 sample means. The sample mean for starting salary for econ majors, sample mean starting salary for theater majors. Right? So that very first group, right? That's maybe the econ majors. There is a true population mean and a population variance. I probably can't see the population mean. I only have a sample. So what I know is going to be true is that what we had been doing. Maybe a little light. I'll switch over. Let's say that my econ major. We're thinking about that sample mean should be normally distributed around whatever that true population mean starting salary for econ majors is. Well, I can take a sample. I've got a certain sample size. If I know the population variance, whatever sample mean I saw, I can turn into a z-score and find the probability that I saw that, if in fact what I assume the feature is true, or even if I could see the population mean, I could determine how likely or unlikely it was for me to see that sample. We then have a second group, right? Maybe this is going to be our kind of theater majors here. So on the same, like we're just using this x-axis for the value. So if I think about the distribution of the sample means for my theater majors, maybe it looks something like this, right? And maybe it's distributed around slightly lower average. So can I say anything about the difference between those two sample means? We can kind of think about this. What's the most likely, right? If I could actually observe the population data, what would be the most likely difference for me to see between 2 sample means, right? One from each of these groups. Well, if this is the most likely value for me to see for theater majors, and this is the most likely value for me to see for econ majors, you can think about when I'm looking at the difference here, can I say anything about the distribution of the difference in those sample means? Well, whatever this difference is, that's going to be the most likely difference for me to see, right? These two values are the most likely values for me to see, these sample means. So that'll be the most likely difference. So whatever that value is, you know, I don't know, maybe this is 45,000, this is 50,000, just to put some numbers to it. So the most likely difference for me to see would be 5,000, right? Or whatever that difference is between the population mean for each group. So I can think about that's the most likely outcome for me to see is that difference in the sample mean of 5,000. And what's the most likely outcomes from there? Well, this difference here or this difference here. So all these differences that are really close to 5,000, a little bit more or a little bit less. So all these differences, these values are a little bit above 5,000, a little bit below, still pretty likely for me to see, but not quite as likely as seeing that 5,000. And then how likely is it for me to see differences that are like way out here? Well, this has a low probability of occurring, this has a low probability of occurring. So the probability I see a difference of something like, I don't know, we can think about them this way. So I don't know, 10,000, right? is going to be really, really unlikely. And the probability I see that difference be negative 10,000, right? Theater majors have more. Really, really unlikely. And I can build out all the probabilities in between that range as well. And what ends up being true is that difference that I'm looking at, the difference in those sample means, ends up being normally distributed around whatever that true difference in the population means is. So now it just goes back to I've got a normal distribution. So if I've got a normal distribution, right, we can start to say things about how likely or unlikely it is for us to see certain differences in those sample means. Okay? So here's where I probably haven't really seen something like this. I kind of already identified that the mean of that difference in sample means, right, is going to be centered around whatever that true difference is. So when we start out drawing our distribution for the difference in these sample means, it'll be centered around whatever that true difference is. Okay? Now, before we had one population, the other thing that we were interested in was the standard deviation of our sample means. Well, now we'll have the standard deviation for the difference in sample means. Well, if you think about this here, I'll do the econ majors just to, so, sample means for econ majors. Right? So we know that from that one population examples we worked through, that the variance of our sample means will just be the variance of the original data divided by the sample size that we took. Right? And that'll exist for the theater majors as well. Okay? So if I want the variance, I'll get out of the way here in a second. This would be E, this would be a T. So if I want the variance for the difference in those sample means, all that's going to be is just add up these two variances. You're going to add up the variance from each sample mean. So we've got the variance of that sample mean on econ majors plus the variance for that sample mean for our theater majors. Okay? So now we've got a normal distribution. We know what it's centered around, or we know the mean of that sample difference. And we now know the variance for that difference in sample means as well. Now, if we want the standard deviation, what do we have to do? Simply take the square root. So to get the variance of the difference in sample means, you just add up the variance of each sample mean. Then if you want the standard deviation, just like before, we just got to take the square root. Okay? Well, now that I have all this, I might be able to think about how can I build a confidence interval using the sample difference that I find, or the difference in the sample means that I find. Okay? If I wanted to do that, let's try to relate it to what we did before and try to build it out. I think what was so before we took our sample mean, we added and subtracted a certain number of standard deviations away that we wanted to go to the left and the right to build this confidence interval. We then multiplied that by the square root of population variance over the sample size, where what this really represented was just the standard deviation of my sample mean. So that's what we just got done doing in the last exam or the last kind of stuff. So now I'm trying to build a confidence interval for the difference in these sample means. So instead of my confidence interval being centered around whatever one sample mean I see, it's now going to be centered around the difference that I see. You can almost think about it as you want to. And we'll all kind of use this d hat to represent the sample difference. This is the sample difference that we see, or the difference in the sample means that we saw from these two different samples that we took. So we're really just building a confidence interval. It's just going to be centered around the statistic we're interested in. We're no longer just interested in one mean. We're now interested in the difference in the sample mean. Now, what we really want to know is what's the true difference in the population means, but we can't observe that, right? So we're using our sample to build a confidence interval about where that true difference is. What values could that difference be with different levels of confidence? So the next thing that we're going to do, and then right? Here, we're starting out with examples where we know the population variance. So if we know the population variance, the rules don't change. It's just like one population. We can still use that standard normal distribution. So I can use that standard normal distribution to determine how many standard deviations away that I want to go to build my lower and upper bound. And then here, before I was multiplying by the standard deviation of the statistic I was interested in. So I'm going to do that exact same thing here. I'm going to multiply that by the standard deviation of the statistic I'm interested in, which is the difference in those sample means. What is the equation we have for the standard deviation of the difference? We said it's just the square root of adding up the variance from each one of these sample means. So just plug that in. And really, from what we knew before, the same rules apply, right? We build our confidence interval around the statistic we're interested in. It's just now the statistic we're interested in is the difference between two statistics. And then you add and subtract a certain number of standard deviations. Well, if I want to go 2 standard deviations away, I take 2 and then I multiply by whatever the standard deviation is. So the only difference now is that equation for my standard deviation of the statistic I'm interested in has a few more moving parts. But really the principles of what we're doing, everything is exactly the same. Questions on this? We'll put some numbers to it here. Any questions okay with this? No? So, you know, we basically have our confidence interval equation that we just kind of built out, trying to relate it to things that we've already talked about. And we can, from here, it's really just a matter of, I've got 2 samples. As long as I'm given the population means, once again, we're starting out with a scenario where it's not very likely that we have population variances, but not the population mean. But we'll start out with these and then see, okay, what's the more practical one, which is when we only have sample variances. And it becomes a little bit more complicated than when we have one population. So really at this point, once I have my 2 samples, I can determine my sample size, I can determine my sample means. I looked at Z value up the exact same way I did when we were building confidence intervals before. There's not a whole lot that has really changed here. So we've got all the same steps that we did before we were building confidence intervals. It's just now we have like twice as many, right? We've got 2 sample means, 2 population variances, and 2 sample sizes. Okay? We'll still call what we're adding and subtracting to our sample difference, the difference in sample mean. We'll still call this our margin of error. I'm just gonna have a nice term for it. So let's try to kind of work through this now that we have that confidence interval equation. Let's try to build that confidence interval for the difference in salaries for econ and theater majors. Okay? So I've got 40 econ majors. I've got their starting salary of $45,000. I've got 50 theater majors starting salary of $33,000. And then I was somehow given the known population variances here. Then I build a 95% confidence interval for the true difference in starting salaries is. And I can do this for any majors, right? If I go out there and grab some sample data, I can do this for anything. So what we're going to do is first think about, okay, what's my first group and what's my second group? Well, here, the way that we'll define this is I'm looking at the difference between econ and theater, so I'll keep econ as kind of group 1. From there, it's a matter of plugging our values in, right? So my sample mean from group 1 was 45,000 minus the sample mean from group 2, 33,000. So I can think about my confidence interval is going to be centered around what sample difference did I find? 12,000. Right? So if I had options presented to me, it should be that the confidence interval, right, is centered around this value of 12,000 because that's the sample difference that I found. Now, we'll skip the Z value for right now and just plug in everything else we know. All right, so we need to multiply whatever that Z value is by the square root of the first group's variance, which was 9,000, over what was my sample size for the first group. Looks like I had 40 econ majors. And then add to that the variance of my second group divided by how many theater majors did I have? 50. So all I'm really doing here, once I've got that form of terms, is plugging in the values. So the kind of, I guess, more difficult part of building a confidence interval, or the thing that hopefully we're getting more and more familiar with, is that we now need to look up that Z value, okay? So if I want the 95% confidence interval, what's my alpha value there? 5% or 0.05, right? So let me go here. We've got our Z values. Pull these up. So I want 0.05 outside of my interval. And the equation kind of reminds me that means how much is on each side will have of alpha, 0.05 divided by 2. So I'm going to look up, right, alpha over 2, which is 0.05 over 2 or 0.025. So I go to my standard normal table. I see what value is closest to 0.025. Well, I can actually find that one exactly. I go over negative 1.96. Once again, this is where the positive and negative are really already built into our comparable equation. We're going to go 1.96 standard deviations above our sample difference with the upper bound, and then subtract 1.96 standard deviations or go below 1.96 standard deviations here in the lower bound. Okay? So all I have to do now, plug in that value of 1.96. Any questions kind of over any of the steps there that we just worked through? Now, what could I have also done if I didn't want to use these Z tables? I could have used what I think is like a shortcut, but if it's, some people, it doesn't ring as true. I could have actually just looked up 0.025 on my student T table, but remember that the last row is telling me my standard normal values. So notice if I go down to that last row, I get that value of 1.96. Either way, we'll come up with the same value there. Just kind of a shortcut using that last row to get my standard normal values from that student T table, right? It's like two tables almost built into one. Okay? So really everything we did there, right? Once we have those values plugged in, it's just a matter of computation, right? Getting this into our calculator. Questions? Okay with this? All right, so this one, I chose some variances to just have some nice numbers. Also, like it's one of those practical things where there aren't known population variances, so like I kind of have to make them up or just kind of use some of these numbers for example. But you'll notice I have a really tight kind of confidence interval here. Like I can say that the true difference is somewhere in that range. That's probably a little bit unpractical. It's probably more likely I get something like this. So maybe I see a sample difference of 12,000, but I've got really high population variance, right? In practice, when I'm looking at salaries, I mean, if the averages are something like 45, I could potentially see sample means that are off by a couple thousand, right? Well, then when I'm thinking about the differences, like we're squaring things, I mean, this can get very large, right? So maybe I've got really large population variances, and maybe I don't have as high a sample size. Maybe I have only 30 of each group, right? So if I have really low sample sizes, really high variance in the original data, maybe I get this really wide confidence. Remember, what are some of the things that change the width of our confidence? If my population variances are higher, that's going to increase the standard deviation, which means I'm adding and subtracting a much larger value. If I have lower sample sizes, I'm now dividing by a smaller number here in the denominator. These are also going to go up even higher. So if I have really low sample sizes, really high variance in the original data I'm sampling from, I'm going to get these really wide confidence intervals. So maybe I get something like, even though I see a sample difference of 12,000, maybe, let's see, so maybe it goes negative 2,000 to 26,000, right? Not a very useful confidence interval if this was the case, but I'm just using it to make a point. Okay. If this instead was the confidence interval I found, the problem with this is, what can I say here about the true difference between econ and theater major starting salaries? Well, the true difference, right, could be a pretty high positive value based off the sample means I saw, but it also could be negative, which would imply what here? Remember, we took kind of econ minus theater. So if I have a negative value for that true difference, what would that really be saying? Yeah. Yeah, that theater majors will be making more than econ, right? That's the only way that difference, right, is negative. So the problem is, if I had a confidence interval like this, well, maybe the true difference is that theater majors make more. Maybe the true difference is that econ majors make more. Or maybe there is no difference, right? Because 0 is included in that confidence interval. So kind of like with one population, but even more so now that we're looking at difference. If I have a confidence interval that only has positive values, that's interesting. If I only have positive values, here I could say that with 95% confidence, econ majors have a higher starting salary. If I had a confidence interval like this that went from -2,000 to 26,000, I can't say anything in terms of what the true difference, at least with 95% confidence, I can't say anything about that true difference between the two groups. In fact, with 95% confidence, I can't even tell you that it's different than 0. Could be that there's no difference there, because that's one of the possible values. This confidence interval represents the possible values for what that true difference is. So the interpretation of these confidence intervals starts to become a little more interesting, especially if they don't cross over that 0 point, right? Now, if they cross over that 0 point, it's like, well, maybe the true difference is positive, maybe it's negative, maybe it's 0, right? So maybe theater majors make more, maybe they make less, maybe they make the same as econ. Questions over anything there? All right, so let's try something like this. Are we on time? So we got what, 20 minutes? Okay. I think what I'll have you do here, I'll have you guys work on this one, just to get some more practice with confidence intervals. Also for showing up to the class after the exam. Right? So let's say I have the same sort of setup, right? I've got my confidence interval equation over there. And I'm looking for the difference, or the true differences between Indiana and Ohio. Was it robbery? Yeah, robbery. So this one's a little goofy, but this is something that we can do. So let's say I have 24 years of data for each state. So here, my sample size for each group is exactly the same. I've sampled 24 years of data for each state. So my sample size for Ohio and my sample size for Indiana are both, what, 24 years. I'm giving you the population variance of robbery rates in Indiana is 175, and the population variance for Ohio robbery rates is 497. And this is all like per 100,000 people, so we're kind of comparing apples to apples, right? We're accounting for the population. So I take the sample from these sample years, I find the robbery rate in Indiana was 109, and I find the robbery rate in Ohio is 163. So if I'm looking for the true difference, right, between Indiana and Ohio, so that's how we're going to set it up, right? The difference between Indiana minus Ohio. What would that 95% confidence interval be? Now, we're following along. My alpha, right? The previous problem, we also built up 95% confidence interval. So from what we were just talking about in the previous one, we should actually already know the z value here. But if not, you can look it up in that table. We're going to do a couple minutes to work on that. Talk with the people around you. Try to start getting used to like entering these in your calculator, because with these two population examples, there's more moving parts. It's a little bit more tricky, right? If you're trying to enter this all at one time, I would kind of maybe suggest breaking it down into parts, right? So once you plug all your values in, maybe find this first, right? Then multiply that by whatever your z value is, and then kind of take that value, add it to your sample difference, the difference in sample means that you're upper bound, and then subtract that margin of error to your lower bound. Okay. So I'll give you a couple minutes to work on this one, and we'll kind of talk about it together. Yeah, so our sample size here, we got 24 years from each state. So before we had like 40 and 50 theater majors. Now we're going to have 24 years and 24 years. So this one's kind of nice and easy where you've got sample sizes that are the same between these two samples you took. Yeah. It's because it. Give me 1 second. I think I know what might be wrong. Okay. I don't know why it's disabled for some reason. Why is it disabled? Okay, so in light of that, what I'm going to do is anyone who has a read at the end of the class, make sure you give me your name, and I'll just give everybody full points. I don't know why it's not. It's set to be enabled. I don't know why it's not getting here. So, and then everybody else, actually, let me reopen this, and I'll just kind of get you to respond so I can identify everyone who's here. We can get kind of points on the day. Sorry about that. Let's see if it actually works when I start this new session, maybe. Is it still not showing up? Okay. So everybody else, just kind of make sure you get a response in here. Even if you responded before, make sure you respond again. I'll give you guys 10, 15 seconds to make sure you get everyone here. I think I counted it 24. So 24 minus however many of you have a read. Drew, make sure they got a response in here. All right, close it out. And like I said, everybody got their answer? All right. So everybody who has a reef after class, just kind of, I'll jot your name down so I can update it manually. Okay. So if I'm looking at this, right away, which one of these can I rule out right away? A little bit easy to identify here. D. So why? What should this confidence interval be centered around?
It must be negative because if you're starting out with the mean being 109 minus 163, you'll end up with negative.
Yeah, right. We're looking for the difference between Indiana and Ohio, right? So the sample difference we found, well, if you just look at the numbers, Indiana's here is 109, Ohio's 163. That difference is going to be negative, right? Indiana had a lower robbery rate than Ohio, right? So right away, if I look at that sample difference, that's what I'm centering my confidence interval around. I've got what? Negative 54 was that sample difference I found. So my confidence interval should be centered around that value. Okay. From there, it's a matter of what Z value, right? Remember Z value is the alpha over 2 on either side. What we said, it's the same confidence interval I used before. The 95% level alpha is 0.05. So I'm at 0.025 on each tail, so that Z value should be what? 1.96. Right? We're using that standard normal distribution to look at the Z values. Every time I have a 95% confidence interval, I'm looking at the same alpha over 2 value. For confidence intervals, I'm going to always have the same Z values there at the whatever level of confidence I'm looking at. So we just did the 95% confidence level one. So it's going to be the exact same Z value used in the previous problem, which was 1.96. It was actually here on the board before I erased it here and started working. From here, it's a matter of plugging everything in, right? I've got 24 years for each group. The one group's variance was 175, the others was like what, 427? Yeah. Okay. Now submitting getting entered into our calculator. So kind of like with the one population one, sometimes I would mention, maybe prevent yourself from making calculator mistakes. Working backwards here sometimes helps with order of operations. So if like I take this, divide by this, add 175 over 24, take the square root of that value, multiply by 1.6, and then add it to whatever sample difference I found. Sometimes that can make it a little bit more easier, kind of breaking it down into parts like that. Right? So we've identified everything we kind of needed. We got that Z value. Now it's a matter of plugging everything in. Okay. So hopefully, I know that I end up not just getting credit for just responding here, but we had a lot of time to work on that. So if you were able to complete it, hopefully you're kind of getting these answers. If not, then you just need to make sure that you work through more of these, make sure you're comfortable using that calculator. Like I said, maybe breaking down into parts makes it a little bit easier there. So with 95% confidence, we recall that I was looking at the difference between Indiana and Ohio. Right? What could I say with 95% confidence here? And we're looking at robbery rates. So with 95% confidence, I could say Indiana has blank robberies than Ohio. No one can fill in that blank. Yeah, right? If I see that all the values in my confidence interval are all negative, and with 95% confidence, I can say the true difference in robbery rates from Indiana and Ohio is negative. What would that imply? So let's say Indiana minus Ohio. I'm saying with 95% confidence, that difference is less than 0. What's the only way this difference is less than 0? If Ohio actually has higher robbery rates, right? Or if I want to, I can rearrange this equation to kind of prove to myself to subtract, right? Mean from Ohio from both sides. And saying that difference is 0 is really saying that with 95% confidence, Indiana has lower robbery rates. Okay. All right, I'm asking too much here. I mean, I know this maybe seems kind of easy. All right, this is like pretty useful. Like if I'm comparing two states or something, and I can find that confidence interval for whatever variable I'm looking at, that the difference is only positive or only negative, I can start to make some pretty strong statements about whatever that application I'm looking at is. Okay. All right, so I'll introduce hypothesis testing here. These differences in two populations. So we can do it with means or proportions. We're just going to call that true difference. So I think before, I might have erased it over here. No, I didn't. Right? We're thinking about the difference in the sample means we found. Let's think about that as our sample difference. Right? So there is some true difference here. So when it comes to hypothesis testing for two populations, we're going to have 3 different types of tests, just like we did before. Right? So we're going to have a right tail, right, assuming that difference is above a certain value, left tail, assume that difference is less than a certain value, and a two-tailed test. Sorry, did I say two-tailed? Right tail, left tail, two-tailed test. Okay. Everything works exactly the same as before. We've got 2 one-sided, 1 two-sided tests. So we'll come off e-values and start multiplying areas by 2. It's a two-tailed test. Think about critical values. They're always going to be right for a greater than or right tail test. They're always going to be negative for a left tailed or less than test. They're always going to be a pair of critical values at every alpha if we have a two-tailed test. Right? Same value with 1 positive, 1 negative. Now, one thing I'll do to make this a little bit easier, but also in application is usually what we're doing is we're going to use this assumed true difference value. Before, when we had like assumed true means, we're looking at comparing against a whole bunch of different values. For the assumed true difference, we're going to always keep this at 0. Right? So when you go through and get to the final, right, and you start to work through problems in class, we're always going to use this assumed true difference of 0. Now you can use other values, right? But the reason why we almost, a lot of the time we usually use 0 anyways is because notice if I'm saying, is that true population mean or is that true difference less than my assumed true value of 0, that implies that I'm kind of testing to see whether or not Indiana has lower robbery rates. If I say, is it greater than 0, I'm testing to see, does Indiana have higher robbery rates? Not equal to 0, I'm just saying, are the robbery rates different, right? And those are, usually we just want to know, like, is one group higher, lower, or are they different from each other? Now, if I wanted to use an assumed true difference of something like 20, then get a 20 here, add a 20 here. What I'm really saying is, does Indiana have robbery rates that are lower than 20 of Ohio's, right? Where I'm starting to kind of throw into, now it gets a little bit trickier there. So that's why, Russ, we're just going to keep this assumed true difference at 0, okay? And it makes our life a little bit easier. So we've got all these steps that are exactly the same as what we were doing before, right? We can find critical values, we can calculate our test statistic, we can find p-values. Nothing changes. There's only one thing that changes. We're doing hypothesis testing for 2 population examples. This is the exact same slide I showed you before when we were talking about p-values, critical values, the exact same thing. The only thing that's going to change is this test statistic. So let's think about why, and I'll hand those exams back. So before, our test statistic for a sample mean looked like this. Okay. So all we're going to do to calculate the test statistic for the difference in sample means. Well, now we're no longer looking at a sample mean as our statistic. We're looking at a sample difference, or the difference in our sample means. We'll subtract the assumed true difference, but I just told you we're always going to use 0 here. So if I really want to, I can almost ignore that, right? Subtracting 0 doesn't change anything. And then now I'll divide by not the standard deviation of one sample mean, but the standard deviation of the difference in my sample means, which we had already kind of talked about for confidence intervals, is just going to be the square root of basically each sample means variance. So we'll take group 1, their variance divided by the sample size from that group. We'll take group 2's variance, the data we sampled from, and divided by the sample size we get for that. So it's still following the same procedure, right? Take the statistic you're interested in, subtract the assumed true value of that statistic, divide by the standard deviation of that statistic. Nothing's like changed, it's just that to calculate standard deviation, or maybe the statistic we're interested in, there's just a few more moving parts now. But it's still the same general setup. Once we have that test statistic, we can plot that against our critical values and determine rejection decisions. We can use that test statistic to find p-values. If it's less than alpha, we can make our rejection decision based off of that. The procedure of what we'll be doing with hypothesis testing won't change at all, right? The only thing that's going to change is this calculation of our test statistic, or in this case, our z statistic, right? The test statistic coming from the standard number distribution. Good questions on that. So I think what we'll do Monday is we'll work through a few examples. I'll actually show you how we do hypothesis testing and stuff in Excel. We'll then kind of continue to look at difference in proportions, confidence interval hypothesis testing, and then difference in sample means when we only have sample variances. So I think we'll probably get through all of that next week. And I'll show you Excel examples of each one as well along the way. So I'll get an Excel file up there that we'll start working with next week. And I will start handing these out. I said that answer will be posted by the end of the day. So, Zach. Sarah. Will. Matt West. Yeah. Julia. Kate. Sarah. Floyd. Reese. Kevin. Nate. Will. Anybody else not get one? Oh. You guys can go. Yeah, everybody else. Everybody else.
I really do not know the answer. So it's like,
So, double check. I went through after just knowing about the one question,
I said that because it's
I tried to
I
feel-
did it, even if I was really sick.
Really?
Ow,
I
like,
tried to feel like to do that.
yeah. Okay.
That's what I went through that folder yesterday. And I didn't know. But yeah, send me an email about the basic question. I'll go back through.
I just knew I thought thank you.
Oh. Let me jot your name. Sorry about that. I don't know why it's not
No, it happened to me earlier this semester, and I forgot about it, but my grading will change.
okay. So you are what's your last name? I'll go back through.
Oh, how did you just?
Joey Wyden, yeah. And then you have to read that. Okay.
And also, October 4th.
Is that the same day? Or is it? Okay.
Thank you.
Yeah, if that happens, let me know.
That's
Like I
so
said,
funny.
I had it set, but it's set to enable, so for some reason it's not
It
working.
normally works, just every once in a while.
Okay, so I'll go through and try to make sure it's working.
I've gotten way too.
Okay.
Mine, I wasn't here, but it was excused.
Okay, double check. I went back through yesterday. I think I actually changed it.
Yeah, one of them, the 18th, but I was also gone the 4th.
Okay, I'll, double check that. Okay.
Maddie Gibson or Madeline.
Yeah. Okay, and that's it. All right, thank you. Sorry about that, by the way.